Coming in for round 2 is Dr. Stewart. You were hearing from her earlier.
Hi there.
Hi.
How's it going? I'm about to talk about a slightly different piece that I'd referred to a couple times in the first presentation. So everyone understands what I do about the structure here. I had moved some of the sensors and communication stuff out of Distribution 101 and into the beginning of cyber. And there's a really important reason for that, in that everything to do with the cybersecurity system is related to the communications and data networks. And so I wanted to make sure that basic introduction was there before we delved into things to do with cybersecurity. And again, the introduction here for cyber is mostly around what the words mean, what we talk about when we're referring to industrial control system cybersecurity, and what the components are to be thinking about when you're talking about your strategies or learning about the strategies that different utilities have put in place for the distribution system in particular. So we can get started. Next slide. So like I said, goals of this session were, and you've got me for slightly longer this time, to understand the communication system and its function within the distribution grid in particular. So primarily, again, we're talking about distribution, transmission and distribution when it comes to communications and to cyber are pretty different, actually. And for all the reasons you've heard already, that's for a reason. Then I'll give this introduction of what is cyber and what do we care about with regards to ICS, discussing the operational technology and information technology networks. And again, that's why it's important we talk about communication and the difference in the management of them and the different systems that are concerned. And then I'll talk about NIST's cybersecurity framework, along with some of the work that's been done on the different threat tiers and different types of protections. And again, it's a 45-minute introduction to cyber. But I'm a power systems engineer as well, who just happens to have delved into the world of cyber and understands it from the perspective of how the utility is working with it. And so I just wanted to make sure the goals here were definitely around the sort of understanding of words and background in the system when you're thinking about all the different sessions over the next 3 days. So next slide. So basic introduction to how we measure components in our system. How we get from the point of measurement to the point of visualization of the data. So I'm just describing this sort of picture here of where we start with the variable you want to be measured and how it's connected to the power system. If you consider that to be a smart meter, it's connected to both the communications backhaul for the AMI network, along with the actual electrical communication or electrical connection to your house, for example. So the point of connection where it is on the power system is very important to work out how much data you need to transport and what is useful. And then there's the measurement device itself, be it earlier I was asked about inverters doing measurements, or a smart meter, or an advanced type of sensor that takes over or thousands of samples a second. The measurement device that's being used is particularly important also because of the degrees of accuracy, because you want to consider if you're wanting to run an analysis on the potential of a transformer to fail in the next 12 years, you potentially want to work with higher fidelity data, and so you need to consider also the accuracy at the point of connection as well, because everything is connected to the system generally through some form of measurement device, be that a potential transformer or a current transformer, essentially to get to that point. Then what I'll talk mostly about here is the communication system, how that works, and then there's also a case where sometimes people run local analytics and you never actually see the data, you only actually see the outcome of the data. A good example of that is actually some of the billing data that's done. That is a calculation that is done of the level of current, for example, that you're pulling into your house. And that's actually something that's sent back as a function of other components that are measured. Again, we get to the point of useful information. Everything we talk about is how to get from measured data to useful information, from which people can then take an action. And then there's a system electrical response in there. So if you take an action, for example, there's going to be a failure in the system, we need to take an action. There's then a system electrical response that happens, and a feedback loop that we're back to the variable we've measured to confirm that that action has actually taken place. So there's a pretty solid loop here of things that happen, but again, it's not generally as simple as just we want to measure power, we stick a sensor in there and send the data back. There's a number of other pieces that are important to the system. So next slide. So again, focus here is mainly on the distribution system. Apologies, 2 seconds, I need to move my control panel out the way of my own slide. It's mostly on the distribution system and its makeup, but again, communication systems are critical throughout the system. I mentioned this is focused on distribution, but up to the level of transmission, we have numerous things that would be sent back data-wise, which use generally private networks, the Scada system, a number of other things, and it's connected and protected in a particular way. When we get into distribution and we expand this a little to focus more on the communication system, the types of communication depends on the type of function you're actually looking for. But on a very basic level, we tend to separate protection from metering. If there's a type of measurement you need that's meant to take an action locally, like protective relays would take, you'll focus on being able to send that data within the controlled boundary that's needed for protection. But when you're talking about things like smart meter communications, you want those to go up to the higher level and billing to be sent back to the right people. So we tend to separate those protection networks from the other networks that are used in the system. So essentially when you're standing in a substation, someone might ask you, what sort of comms are you using? And they'll say, well, this is the protection network and this is the billing or revenue metering. So then you know it's a separate measurement system. And that's both for cyber and legal and protection reasons. Does every utility have a dedicated network that they use is something I've been asked a couple of times, and the answer is some do. There's some of the more advanced utilities and or people that have gone further into the world of control for the distribution system have developed their own private networks that are dedicated to that utility, and they can use that for their own functions. Otherwise, utilities can purchase communication networks from external entities. There has recently been a degree of sharing of different types of communication, and also you can have fiber lines dedicated to the utility. It can go many ways. I've done a lot of sensor installation work in the last few years, and often the first thing we're asking, well, is if we put the sensor here, how are we going to get the data back? I'm working with one just now with a large IOU. We have 2 types of sensor going into their utility. One of them captures data, I think, at a rate of 30 megahertz. And as you can imagine, sending that data back it's going to get stuck somewhere. It's too much data to really come back. So there's lots of different ways to optimize that. We wanted originally to use fiber optic, as we were going to pull a new AT&T line actually out to the substation. The cost of that ended up being significant because it was a rural utility or rural substation, sorry. And we ended up running with a 4G modem, but placing data analytics at the device so that we actually can compress and send the data in a way that doesn't just block its own communications. Because essentially, if you think of it as a pipe, at some point you can block that pipe by just sending too much information through it. So, next slide. So I think I might have to click a couple times or it's frozen. I'm not sure. Oh, there it is. So the type of communication, like I said, depends on the type of functionality you need. So again, if you're planning for communications, the best, in my opinion, the place to start is what you actually want to get the data to do once you've got it back. So again, I mentioned the planning processes and roadmaps in here for things like protection versus control. The planning process there that I've done previously for sensing and measurement was what do you want that data to do and how fast you need it. Why would you pick one type or the other? Depends generally on the function. So the types of, I've given some examples here of the types of communication networks that are actually used in those different scenarios. If even up to the transmission system here, if we're talking about generation, secure wireless and radio networks can be used to transmit control monitoring messages. In some cases, those radio networks are literally people talking to each other on a radio for control, but generation generally has radio networks in place. They also use telephone service and things that are called POTS, plain old telephone service, to transmit messages between plants, because in the end you need it to be, for those kinds of systems, the most reliable solution possible. And if that's a wired telephone service, then that's what it needs to be. Consider when we have, in California, we prepare for earthquakes. So consider the fact that we're told often to keep having a wired phone service in our house just in case of an earthquake, because we can't necessarily rely on our cell phones at that point. So same theory there. In the transmission system, we're down to sort of power line carrier, which is using the power lines themselves to transmit information through a type of sensor. Substations can also use radio and wireless within their substations and communicate between the substations. Again, radio and satellite phones can actually be used during restoration and repair, depending on where you actually are. Because the point here is it's not just the devices that need to communicate and be secure, it's the humans as well. They need to actually be able to talk to each other, and that's an actual important piece of how our grid works. In distribution, recently there's been actually a lot of work going towards using fiber optics, especially for controlling load. In some cases, it's absolutely necessary to use fiber because you need the data to be as close to instantaneous between the 2 points as possible for synchronization. But yeah, again, there's been a lot of moves toward fiber, but it's something I mentioned earlier. Transmission has, I think when people describe this, I'm never quite sure I want to say it, but transmission has 100% or more data coming back in visibility. Whereas distribution, I think the last metric I had was somewhere in the 30% visibility. So the trade-off here between the cost of new sensing and the cost of communications needs to be considered when you're putting devices in place. Lastly, we're down to smart grid communications, which essentially is something I talked already, the smart meter networks, possibly control distributed generation into the DER management systems, and also the forming of wireless mesh networks between them. There's a backhaul that's used essentially for the smart meter networks, which can depend on various backbones. But again, that's one of the probably more data intensive features now of the distribution grid is how you pull those back. And so, next slide. So there's one thing that's important to talk about is also the dependency of things now on the communication system working. I mentioned the idea that if two generators, imagine two diesel generators are trying to talk to each other, they need to electrically synchronize to the 60 hertz part of the system and to each other. If they don't, there's a good chance they're probably going to kick each other off the network, and that's not the best solution. So the dependencies of the system essentially to talk to each other are pretty important. One scenario we've looked at from the prevalence of smart devices on the same network as a number of other devices was what happens if you're relying on those distribution devices to actually perform an action based on something they've sensed, but also relying on them at the same time for the billing system and relying on them to send you back information on the outage. There's some work going on here to work out how you monitor the bandwidth of the system. It hasn't really been a huge problem up till now. There's very few cases where that pipe for communications has got blocked in any way. But when you start to look at these more advanced applications around voltage control, local operation, self-healing systems, at what point do we start to get to a limitation on that? How do we visualize that? And what happens if you can't see those communications issues? So you need to be able to see the information to actually do something about it. So how do we monitor that better is kind of the future looking world. How do you plan effectively using a combination of things like distribution planning tools and communications planning tools? How do you plan effectively for your future communications needs, not run into the same sort of world that we did with DER, and that we need to be planning much further ahead, not necessarily just for what's right in front of us. So planning for communications is a relatively new field, but it's something that's growing in importance for most of the utility environment at the moment. Next slide. So just a brief overview of the sort of timeframes I'm talking about and how you make those kinds of choices. If we are considering, this slide is from Sasha von Meyer from Berkeley. Actually, we used it when we were developing micro PMUs years ago to talk about where that sort of data sits. So synchrophasor time stamping being, which was until recently probably one of the fastest type of data you could get back in the utility environment. So the scale here we're looking at is way on the microsecond up to years and decades. So if you consider monthly customer bills, even up to planning horizons for the transmission system, which is in the years and decades. There's a wide range of things that you're measuring for and different phenomena of interest that you might be collecting. And so understanding your communications and control networks with reference to what you're actually trying to get to is the entire point of this picture. Essentially showing that if you have synchrophasers, yes, you might be able to get up to monthly customer bill, but you possibly didn't necessarily need all of that data if your only function you wanted was the customer bills to be correct. So making sure people understand their application, understand the types of things they're able to see and what they're definitely not able to see with their data is an important thing to consider. Some of the other ones are looking at harmonics and transients in the system. Doing harmonic analysis is not that fun actually, but it's something that requires a level of data and a level of accuracy and a very specialized sensor to actually do and to do it correct. And so you can make a mistake in doing a harmonic analysis of a system that can also cost tens of thousands of dollars if you don't have the right data to validate it. So just explaining the benefits of different types of phenomena and timescales and issues that they have there. So next slide. So I'm summarizing here just sort of the types of sensors you see at different levels. Grid sensors include things like current transformers and potential transformers at the basic level, phasor measurement units and micro phasor measurement units, which are measuring voltage and current, magnitude and phase angle, which gives you directional type flow information to work out deviations and things like power flow from the phase angle data. RTUs and IEDs essentially are things that are within substations which assist the supervisory control and data acquisition system down on the left in actually creating the measurements and sending the information back to the utility. In the actual primary distribution system, and I think we've gone over what that looks like, there are things to enable the types of voltage control and fault location that I mentioned earlier, things like line sensors that are determining current flow or current spikes on the sensors. And also fault indicators where essentially there can be conditions where even a field crew person can just see a light on a device sitting on a pole and they know that there's something faulted on that line. And so they know what to do or where to see it, because we still rely on a degree of visual interaction with these kinds of things. And then in homes and aside from the smart meter network, we also have things like environmental sensors and temperature sensors, irradiance, things that can be used to help us forecast better and control different variables in the network. So for example, when you have a 110-degree day in Livermore, we have a problem that we sometimes lose one of the transformers. And so being able to actually focus on that going on, knowing what the temperature is and knowing what you're predicting and having enough data to validate that is important for managing your load further downstream and making sure we can keep going when we need to. So next. So Kevin actually mentioned all of this in the first world when we were talking about the OMS system, the outage management system and distribution management, in that there was old versions of computers before and paper maps can still be used in some places. This is a really old picture now. I think it's 17 years old. But traditionally, the distribution operation center did work a lot by phone. They observed status, they threw switches, they did a number of things with the phone. The phone is still part of our communication system. It's just evolved a little from the rotary phone. But we have expectations of, we see all these new technologies during this kind of training, and you walk into an operation center and generally the real world is a little bit less advanced than all of the new shiny things that you see. And a lot of what we do is about making choices of where the best sort of bang for your buck is and spending in that world. And so at the moment, even if there's a home or a place that does not have smart meter technology, often one of the first ways the utility does know there's a problem is when that customer calls in. That's still a system that exists. Customers do still need to call and say that they don't have power in some cases. Living in California, we've had obviously more incident of that than not. As it turns out, the utility knows most of the time when they turn off our power. But the customers still call in, and other things like power quality issues are interesting there, that a lot of the time a power quality sensor is measuring a waveform, which is something you don't necessarily want to push through your communications network. So that waveform isn't that common to get from a few locations. I just did a project where I carried back about a day of waveform data, and it took a full hard drive to bring it back with me. And yes, I was hand carrying data back with me because I didn't really have a way to send it through our network. So power quality issues are in that scale where it's down on that left-hand side of the graph I showed you, and getting that data back through a communications network is a challenge. And so a lot of the time, the way that people know there's a power quality problem, which is generally something like your lights are flickering in your house, is again, people calling in and still communicating that they have a flickering light, for example. Gradually, on the next slide, sorry, Scada has been introduced to the distribution system. I mentioned earlier the Scada type world, which gives the operators the ability to observe the status of the field equipment through these remote terminal units. Scada platform, as I said, heart of the utility operations environment. Originally, Scada and transmission Scada together were sort of coupled together in the system, making sure that we, and sorry, if you could move the slide on one, that'd be helpful. Thanks. Scada and transmission Scada together were, oh sorry, one more slide as well, were scoped together because it was gave the sort of lowest cost to acquire, to operate and maintain the consolidated network as a secure platform for both the transmission operator and the distribution operator. There was a common infrastructure between them both. So it gave the lowest training requirements also because they could work together and putting that in place. Sorry, one more slide. The negatives of that were changes to the distribution portion of it were causing frequent changes to the transmission portion of it. And the structure of Scada, essentially I'd mentioned, again, this is the more detailed version of the very first picture you saw, where we have your sensors with the measuring physical qualities, the RTUs performing the conversion of the data, the telemetry actually communicating the information, and where they collect the information and do the analysis. So next slide. We can go on a couple, sorry. Okay, so talking through the smart meter networks a little more, and I want to make sure I get to the actual cyber slides because I realize I've taken a little longer than I planned. I think I already described AMI to a degree, but the backbone of AMI is also this communications network. And there's a rate of adoption depending on the different regulatory incentives and understanding what the benefit of them is. Next slide. And I've probably covered most of these, so we can probably step on. I think I carried them in the first one. So